Welcome, students. This is going to be our plate tectonic theory notes. Let me just warn you, if you're watching this in the future, the flu of 2019 was rough. That is why I have this hat on. You should not be able to see my face. It is just awful right now. So, to put you in a slightly more distracted mood, I have my wonderful picture in the background. Hopefully, you can figure it out what we're looking at here. But let's get into these notes. So, plate tectonic theory actually had three stages to get there: continental drift, seafloor spreading, and then really the combination of those two gives us plate tectonic theory. So, what did people believe before plate tectonics? Well, they believed that the continents and everything on Earth was in a fixed position. That is, everything except the stuff that could be weathered, eroded, and deposited. So, they knew about WED, all that kind of stuff. The map of the Earth, though, like with the coastlines and everything, was essentially unchanging. You have the same continent, locations, shapes, everything in the past, present, and future. Everything was just the same. So we call it static. Pardon me. All right, but then this dude comes along. His name's Alfred Wegener. Alfred Wegener was a German astronomer, meteorologist, climatologist, geologist. He's kind of a jack of all trades in the sciences, very much like an 8th grade science teacher. He was the first guy to use weather balloons. He wrote like a geology textbook that was used throughout Germany. And really, he was just a nice guy all around. He just wanted to become a professor somewhere, settle down, have a family. Well, there's that good looking man right there. Yeah. One of the students in years past said, he has such pretty blue eyes, which is weird because this is a black and white photo. So, anyways, here's what Alfred did. He proposed that the continents have slowly drifted to their locations. He also proposed, along with that all land masses were once joined together in some kind of a large landmass called Pangaea or Pangaea, depending on how you pronounce it. If you're British, you pronounce it Pangaea. But Pangaea comes from the Greek pan, which means all, and Gaia or Gaia, depending on how you pronounce it, that means land. So it really means all land. According to his theory, the continents split apart from each other and drifted to their current locations, hence continental drift. Now, when he proposed this theory, he just got a bunch of other people laughing and making fun of him. I mean, can you imagine a continent moving? Just drifting? Yeah, that's kind of weird. So, the thing was, Alfred Wegener had a ton of evidence, and as you guys know, if you're an integrated, evidence is only as good as you can analyze it or interpret it. If you're in Science 8, you should be at the point where we're starting to analyze data and look at evidence, so you'll figure out that analysis is everything. People just had never analyzed the data the way he had. So he really went and he found all this evidence in books already. He didn't go out and collect it himself. He wasn't like Indiana Jones running around in the jungle or anything. But you have this long quote that he wrote here, and essentially what it says is this. Like, look at the data. It's pretty clear. It shows that they were once together and they have moved. We're going to go into just kind of the overarching stuff, but when you look at the specifics of the data, it is very clear that there are just things that can't be denied that the continents used to be connected together. So Alfred, this was his theory of what Pangaea was. All the continents were once together, so epic. A little bit more of a stylized, cartoonish version of Pangaea and its breakup. The Permian, by the way, is right before the dinosaurs came on the scene. Triassic, Jurassic, Cretaceous. Those are during the dinosaurs. And then this is modern day. So here's the evidence that he had. The continents kind of look like they fit together like a puzzle, especially when you look at Atlantic coastlines of South America and Africa. I mean, look at, they pretty much line up. Especially when you take all the water out of the ocean and you look at where they touch the seafloor. Look how nicely it lines up there. Now, why would it be slightly different today on the coastline than what it was in the past? Well, weathering, erosion, and deposition have occurred. So, the other piece of evidence besides just the look, which many of us have probably noticed before, is you actually had these fossils that were on separate continents, but they were the same creature. And they weren't things that could fly or travel long distances. They were things that were pretty localized. One of them was called Glossopteris, and that was a type of plant. and that was found all over the place, including Antarctica. You also have these pre-dinosaur creatures, Mesosaurus, Sinognathus, Lystrosaurus. These were things that couldn't fly, they couldn't swim that far. This one that looks kind of like a crocodile, if I remember correctly, is a Mesosaurus. It was not built for swimming in the ocean, so keep that in mind. It might be able to swim from like an island to another island, but when you look at the map, there's not a lot of islands in here, and the chances of getting from one to the other, not very good. So here's some other pictures. You can see Lystrosaurus and Sinognathus clearly are not going to be able to, walk across the water, and they aren't built for swimming. So, but then you can see the fossil distributions, and he actually used these fossil distributions to put the continents together. And we're going to do that in class if we have not already by the time you've seen this video. Other evidence is when you look at the rock sequences on the coastlines, especially in different continents, they're like the almost same pattern. In South America, Africa, India, Antarctica, Australia, you have this basalt, which is a lava rock, and then right underneath that you have sandstone and shale, all kind of intermixed. And then below that you have this glacial till, which is a rock that is deposited when glaciers bulldoze, and all the stuff they bulldoze just gets dumped. So it's really weird that we have the same patterns in the rocks in totally different continents. Even farther, just for your own edification here, when you look at the tilt of the rocks in different continents, especially like South Africa and a portion of South America, they even have the same rock type, but also the same tilting of the rocks. So why would they have literally the same degree of tilt in them if they, were formed separately? Is it really just that randomness? Probably not. It's pretty much they were connected. So again, a picture showing all these patterns of rocks, a little bit more detail there. The final piece of evidence is that there was different climates in the past in the fossil record. Antarctica has fossilized plants, which means in the past it had to be somewhere warmer. Africa had glacial till, which means that it was glaciated by a big continental glacier, which means it had to be farther towards a pole. How does that happen if the continents don't move? Well, and again, these are pieces of evidence as well. This is with the climate stuff. These arrows point in the direction of these things called glacial grooves or striations, and those are just scrapes in the rock that are created by glaciers going through. So, despite all this evidence, and you guys may have ever had this experience as well, despite very good evidence, he was rejected by the majority of the scientific community. What they said was, well, it's not a perfect fit, it's just coincidence. And then they said, well, those animals must have gotten there because there were land bridges in the past, like really, really big ones, as big as an ocean. And they got wiped out. How? Well, those people said weathering, erosion, deposition. Maybe there's a giant flood, like a Noahic flood or something like that. Why do they have the same rocks in totally different areas that are coastlines that match up? They pretty much said it was coincidence or there was some widespread event, something like globally, which would be pretty significant. And then the weirdest one, why did we have a different climate in the past in Africa and in Antarctica? Well, they created this idea called polar wandering, and it was essentially this, that the poles, like Earth is currently spinning like this, okay? And then every once in a while, maybe it shifts like this. And they didn't have a good reason why, but they called it polar wandering. The poles just kind of shift for some reason. It's either that the axis of the Earth tilts and then tilts back, or it could be something like the sun moves to a totally different location. They couldn't really explain it, but they made it up just to kind of shut him down. But the real problem for Alfred Wegener was we couldn't feel the continents move. Wouldn't you feel something that big happening? And because we couldn't feel it, we didn't really know how to measure it. Because we couldn't measure it, it was not something that we were going to be able to explain. And that's what a real theory needs to be able to do. It needs to be able to explain why we see all the things happening, okay? The things that we see are really natural law, and the cause of those things is the theory. So if we can't put a good cause to it, then we don't have a theory. And he couldn't explain that cause of movement. So Alfred was ridiculed. And it was really sad. But he did finally become a professor somewhere. But here's the sad part. Like right after becoming a professor, he went on a trip to Iceland with a buddy of his, or he was prompted to go to Iceland with a buddy to study the polar vortex, which some of us may be familiar with in the last couple of years. Um, he had already been there. It was like going to be his fourth time. He didn't want to go, but he got kind of suckered into it. And he died collecting ice samples in Greenland. So it's pretty sad for Alfred. He finally gets what he wants. He's still being ridiculed by everybody, I believe, and I don't remember for sure. I believe he had just started a family as well. I don't know for sure. But then he dies. So, and his friend didn't go to Iceland because his friend got sick. So that kind of stinks. So about 20, 30 years go by, and along comes this guy named Harry Hess. Harry Hess was in the Navy in the U.S. He served during World War II, and he helped with a mission after World War II to start mapping the seafloor. We were worried about Soviet submarines at that point, and so we wanted better maps of the seafloor so we could outmaneuver the Ruskies. Now, there were some discoveries, and this is where Harry comes in. He discovered these undersea mountain ridges and mountain ranges that went pretty much all the way around the world. So he reviewed all this information, and he made up this hypothesis called seafloor spreading. Ladies and gentlemen, be prepared. You thought that Alfred was a hunk. Take a look at this guy. Yeah. Oh, he looks good in uniform and a suit. Very good. Well, anyways, here's seafloor spreading. We had sonar at that point in the 1950s, and we went around the world. We mapped the globe. And we found you can see this black or dark blue scar that goes all the way around the world. And that is that ridge or mountain system that I was talking about. It's called the Mid-Ocean Ridge, and it goes around the whole world. It's kind of weird. It has a mirrored profile, so if you were to cut it in half, and let's pretend over here is North America, and then this is Europe over here. You can see in the middle it kind of dips down, but it's like a mountain. It gently slopes and then gets flatter. It's kind of the same pattern over here. Here's the idealized version in the Atlantic, okay? In the Pacific, it's slightly different in that it just comes up to one nice point and then dips back down. So again, here's the idealized one. You have this mirrored profile where there's a rise in the middle and there's a tiny little rift, which is an indentation. You can see it really big in the Atlantic one. And then on the sides, you have these abyssal plains, these nice flat areas. So it's the same pattern everywhere. That doesn't happen by chance. So the other thing we found out was really hot down there. When we started probing for the rocks down there, we figured out that when you get closer to that mid-ocean ridge area, it is hot. The farther away you get from it, the colder it is. Now, we're not talking like boiling hot, unless you get really, really close to it. But it is noticeably hot, okay? You gotta remember the bottom of the ocean is super duper cold. So it was discovered that it's hotter near the mid-ocean ridge and colder as you get closer to the continents. Weird. So here's what Harry proposed. He proposed that hot, low-density material in the mantle rises up. And that comes up at those mid-ocean ridges. The material solidifies, becomes rock, and then the stuff that doesn't solidify kind of goes outwards and drags the seafloor sideways because it has nowhere up to go, okay, because it's already plugged up. It goes sideways and drags the seafloor apart. Now, as it drags the seafloor apart, a tiny new crack forms and some of the stuff comes up, solidifies. And so over time, the seafloor spreads apart. The older seafloor moves away in opposite directions. And so that would allow us to have this mirrored profile. And this supports actually how the continents can move. So this was justification for Alfred Wegener. Here's a super sweet diagram showing how this happens. You have all this hot material in the mantle, and we're going to talk about how this stuff rises up. Some of it makes it up through the top. But all this pressure does push the land upwards, hence that ridge in the middle of the ocean. Some of it solidifies, makes new seafloor, but a bunch of it can't make it up there, so it just kind of spreads out. Spreads out this way, spreads out this way. And as it does, it drags the crust with it because it's pretty high friction. This stuff is not like liquid, low viscosity. That means like thickness of the liquid. It's very high thickness. Think like blacktop. When they lay blacktop, it's technically a liquid. Like they pour it into a hole, but once you put it under like a little bit of pressure, like it's kind of a solid-ish. That's what we call a plastic. Okay, it has properties of a solid and a liquid, so it does pull the crust with it. Here's more evidence that they found afterwards. Besides the fact that it encircles the globe, that mid-ocean ridge, if you start sampling it, it has less sediment when you get closer to the ridge center. That means that, it's younger pretty much because it takes time for sediment to fall. If you have less of it, it's younger. If you have more sediment, like out here, it's older. The same is true with fossils. We have very few fossils near the center. We're talking microfossils, things that are like microscopic creatures in the ocean, so they die and they fall to the bottom of the ocean. We have very few of those near the center of the ridge. We have a lot more as you get farther and farther out. We sent this expedition in 1968 called the Glomar Challenger, and we actually wanted to see what the ages of the rocks were. Younger rocks were found to be near the mid-ocean ridge, as expected. Older rocks were near the continent. Now, even weirder, the age of the ocean floor mirrored itself on both sides of the ridge. This is just like everything else. It's been a mirror image, one side to the other. So here's the pretty picture. We're going to look at the mid-ocean ridge. The younger colors, which this is in millions of years, they're towards the center of the ridge. The older colors are towards the continents. This just shows that seafloor spreading occurs. So more evidence is this thing called paleomagnetism, and this needs explained. When rocks form, they take on the magnetic profile of the Earth at that time. Now let me explain that. If a rock has iron in it, the iron either lines up with the magnetic field pointing this way or this way, okay? Depending on what the Earth's magnetic field is doing at the time. But the magnetic field of the Earth, like right now, magnetic north is up there, kind of, well, it's a little south actually. But every couple thousands of years, for some reason, it switches. And we don't need to know why, it just does. But when it switches, the iron that was in the rocks, if it's forming a new rock, like if lava with iron comes up and it starts to solidify, the iron lines up pointing the direction that the Earth is pointing. So the pattern mirrors both sides of the ocean floor again. So let's take a look at the picture. So like this stuff that's coming up right now at the mid-ocean ridge, it's lining up with its magnetic field kind of like our Earth's is today. And like I said, everything's pointing to the south. I misspoke a little bit earlier. So everything formed from lava today points to the south. But if you go farther out, like here and here, everything pointed north. And it keeps this alternating pattern that is mirrored on both sides. Okay, more evidence for seafloor spreading. So like we said earlier, seafloor spreading explains how continental drift occurs. So it's kind of like a, not a mashup of their theories, but it's like a, I don't even know what the music terminology is called. A collab. Yes, it's a collaboration. Yeah. All right, so here we are. Plate tectonic theory. What is it? It's a combination of both theories, like I said. Here's what it says. The lithosphere is broken into tectonic plates. This is different from continental drift because it says only the continents move. The lithosphere, okay, each of the plates in the lithosphere can be made up of continental material and ocean floor material. That's the difference. But these big plates, they drift across the upper mantle, which is called the asthenosphere. They collide, they can divide, and when they do that, they create the major landforms on Earth today. What is the cause of these plates moving? We got into it a little bit earlier with Harry's idea, but it's been confirmed now, or mostly confirmed. It's caused by convection currents. in the upper mantle, in that asthenosphere. When you have heated material, it flows upwards. So the center of the Earth is really hot. Most of us know this. It flows upwards. Okay, the asthenosphere does. When it hits the crust, some of it can puncture through, form new crust, but most of it spreads outwards because it's got nowhere else to go. As it spreads outwards, it drags the lithosphere with it. So it drags that crust apart. The asthenosphere material cools and sinks down again at some point. Okay, so when it's farther away from its heat source and it's been going and pulling the crust apart for a while, it just loses its energy source. So it starts to cool down, but then it starts to sink again because it's higher density. And high density stuff, cold stuff, typically sinks. The exception to that is ice, which we can talk about some other time. And this cycle just continues to repeat. As the sinking material gets lower, it gets heated up by that interior of the Earth again, and then it rises. And then it spreads out, and then it cools off and sinks, and then it heats up and rises. And this cycle keeps going on and on and on. Now, this is the picture. I want you to remember the rising action happens here. And what was this area where the Earth is spreading its crust apart? That's a mid-ocean ridge. Where does it sink? It sinks at these areas called trenches. Okay, we'll get to that a little bit later. One note that we want to talk about real quick. What is it that actually heats the interior of the Earth? The reason why the Earth's interior is a little bit warmer is because it has this material inside of it from its formation called radioactive material. When radioactive materials break down, they give off heat. And that process is still happening today. So radioactive decay is what gives us the heat inside the Earth. Plate tectonics explains mountains, earthquakes, volcanoes, and all sorts of other geological things. So we can use these things to find where the plates are. There's no magical line when you look on, from outer space down at the Earth. There's no magical line that shows, oh, here's where the plate is. You can see the mid-ocean ridges, but there are other things that you have to look at to figure out where the plates are. So using all those features, and this is our next step, we will figure out where the plates are and what kind of plate boundaries we have. So if you have any questions, please let me know. Our next stuff that we're going to be doing is taking a look at what features we see and what that tells us about the type of plate boundary. So hang in there. I'll see you soon. I hope you don't get the flu. Bye.